do anything. Today, we are going to be learning about the quantum numbers, okay? Quantum numbers. And this has a lot to do with the electron configuration. Quantum numbers are 4 numbers that will help to somebody's mic is open. Let me, Mark, thank you. Thank you, Mark. All right, so the quantum numbers will help you to locate an electron in one atom, within an atom. Remember that we know that the protons of an atom are inside of the nucleus, and I'm gonna draw this. This would be the nucleus. But the electrons, protons and neutrons are inside of the nucleus. Now, electrons are in the orbitals.
So, Mr. Correa,
Yes, Chastity.
we are being evicted right now, so like we get like come out for a good 2 minutes, I guess, to walk up to your classroom. Yeah, good luck.
Oh, so you're gonna be kicked out now.
Yeah.
All right, I'm gonna stop this. I'm gonna pause the recording now. All right, so I was talking to you about the quantum numbers. Now I'm gonna share with you which are these 4 quantum numbers. As I told you, they are useful to locate an electron, to describe electrons within an atom. I'm telling you that you know that protons and neutrons are inside of the nucleus of the atom, while the electrons are surrounding the nucleus of the atom. And they could be surrounding the nucleus of it, close, very close to the nucleus, or far from a distance. And still, we can say that they are surrounding this nucleus. Now, there are 4 quantum numbers. And as I told you, this is like the electron's address. This is where you can locate an electron. This is what describes the position and the amount of energy of an electron. Actually, the position of an electron depends on how much energy they have. If they have very low energy, they will be close to the nucleus. If they have a large amount of energy, they will be further from the nucleus. Okay, so the 4 quantum numbers are these. The principal quantum number, which is represented with the letter N, and as it says here, it specifies the main energy level or the orbit. Okay, we have the azimuthal here quantum number, which is represented with letter L. This is in Greek, lambda, but it's L in the Arabic alphabet. In our alphabet would be the letter L, L for lion. It shows information about the sub-level, okay? The sub-level. And the magnetic quantum number, represented by the letter M, represents the orbital. While the spin, this is a mistake, it's supposed to be an N. Spin quantum number, represented by the letter S, refers to the movement, the spinning of the electrons, okay? Now, this might look very confusing at first, and that's why I'm gonna take the time to explain this with details. We go to the first one, the principal quantum number. This, once again, refers to the size and the energy of an orbit of the energy level. Remember that in the Bohr structure, we represent the energy levels with these rings, with these circles around the nucleus. Let me ask you, how many electrons do you remember that fit here in this first energy level? Hello?
2.
2 electrons here. How many fit here? Do you remember how much?
8.
8, and so on. And the next one is going to be 18. So as the electrons are further from the nucleus, that means they have more energy. One electron that is here have more energy than one electron that is here. And this has more than one that is here, okay? So in other words, the greater value of N, where N represents the energy levels, the numbers that you put in front when you are writing the electron configuration, this N, the greater value of N represents bigger orbits with high energies. And also distance from the nucleus increases, right? So I didn't tell you this before. I wanted to get to this point before I told you that, and I'm gonna tell you now. This is energy level 1, which is N1. It's also called K, okay? You don't use K when you're writing the electron configuration. You instead use the numbers, okay? 1, S2, 2, S2, 3, S2, P6, blah, blah, blah. But you can refer to these layers, to these energy levels with these letters, K, L, M, N, okay? And this is the number of electrons that fit in them. At first, I just told you how much was the number of electrons that they could hold. But there is a mathematical equation for it, and this is the mathematical equation to determine how many electrons fit in any energy level, which is 2 times the energy level squared. So if you're in the first energy level, how many electrons fit there? Well, 1, because you're in energy level 1 squared. 1 times 1, that's still 1, times 2, is going to be 2. For the second energy level, I'm going to have it here within parentheses, 2 squared, that is 4 times 2, which is 8. For the third energy level, 3 squared, which is 9, times 2, 18, and so on. And after the fourth, fifth, sixth, seventh is going to be the same. 32 electrons is the most you can hold there, right? This second energy level talks about the sub-level. Remember that the energy levels, one has only one sub-level, S, but energy level 2 has 2 sublevels, S and P. Energy level 3 has 3 sublevels, S, P, and D, etc. So L, lambda here, the azimuthal quantum number refers to the sub-level of energy. And these are the letters that we have always used for them, S, P, D, and F. For those that wanted to know what these letters stand for, this is what they mean. S is for sharp, P is for principal, D is for diffused, and F is fundamental. All right. As you know, this is the number of electrons that you can have in S you can have 2, in P you can have 6, etc. Now, when you're writing the quantum numbers, you don't write letters but numbers. So there are numbers associated to these sublevels. If you want to talk about sublevel S, you say 0. For P is 1, for D is 2, and for F is 3. And we are going to do one example of this. Let me just move to the whiteboard so that we can do one example of this. Let's take, for example, any element. Can anybody give me any element, whatever you want, please? We're gonna use carbon. Okay, carbon equals 6. So if we do the electron configuration for this guy, we're gonna have the 1s2, 2s, wait, 2s2, p6. Oops, I already passed. 2s2, p2. There we go. Now, if we want to talk about the quantum numbers for carbon, we will always focus on the last electron that you placed here. What is the last electron that you place? Where is it? Here, isn't it? It's one of these 2 electrons that you put here. Remember that these numbers is the number of electrons that you will find in this sublevel within this level. Okay, you have 2 electrons here in sublevel S within the energy level 2. Now, this was not the last one that I placed. It was here. So if we want to talk about the quantum numbers for carbon, we basically are saying to talk about the last electron that you placed. And remember, it's 4 quantum numbers that we call N, L, M, and S. N is the energy level where this electron, where the last electron is located. In which electron is located this, I'm sorry, in which energy level is located this electron that I place here? What is the energy level where you find it?
The second.
I'm sorry?
The second.
Second, or energy level 2. Thank you. Now L, or the azimuthal, refers to the sublevel. In which sublevel is placed this electron? What is the sublevel where you find it?
1.
No, these
P.
are the sublevels, S, P, D, and F. So the sublevel is P. You find it in P. The number that you will write when you are talking about P is 1. So L in this case equals 1. Am I correct? Yes, because it's in P. Now M, and this is the most complicated part, and that's why I need you to pay attention to this. We're going to see it with more details later, but for now, please look at this. The sublevels have orbitals. Orbitals, these are the circles that surround the nucleus of the atom. And it's not only one in one sublevel. Let me tell you something that you need to know in order to understand this. Every orbital can hold up to 2 electrons. So in sublevel S, where you can have 2 electrons here, you can have 2 electrons. How many orbitals do you need to hold 2 electrons? I will repeat the question.
1.
Just one. Why? Because in one orbital, you can have 2 electrons. Now, P, how many electrons fit in P?
4. 6.
6. How many electrons fit in P? 6. Okay, this is the number of electrons that fit in P. Now, for 6 electrons, how many orbitals do you need?
3.
You need 3. That is correct, 3. Now, in D, how many electrons fit? 10. How many orbitals do you need to store 10 electrons?
5.
5. That's very easy. I mean, you shouldn't be confused on that matter. So in S, you can have only 1 orbital, but in P, you will have 3 orbitals. In D, you will have 5 orbitals. In F, you will have 7 orbitals. Now, orbitals are represented with boxes like this, okay? So S would be 1 box because here you can have 2 electrons. Now, P, for example, will have 3 boxes. Let me see if I can move it to have it more center. For P, you will have 3 boxes, and I'm gonna do it like this. Okay, 1 and 2. Wait, hello, yay, there we go. Okay, you have 3 boxes for P, all right? And for D, how many boxes would you have?
5.
5. 5. Now, this is how you represent the electrons. Electrons are represented with arrows, okay? And the arrows will be pointing up or pointing down, okay? So, where you have 2 electrons, you will have 2 arrows, one pointing up and the next one pointing down. So, S here, the first energy level, that has only one sublevel, will be like this. The second energy level would have 2 sublevels, S and P. By the way, let me draw S here, which is 1 box with 2 electrons, one pointing up. I'm going to explain this about the pointing up and pointing down, etc. in a minute, because this is the last energy, the last quantum number that we have here. Now, in P, remember that in every box you can have up to 2 electrons, but there is a rule that says that you cannot have 2 electrons in one orbital if you have space, if you have empty space in the other orbitals. So you will always semi-occupy the orbitals, and then you will start putting the next ones here. So you will have one here, and the next one is not going to be next to it. It's going to be in the next orbital. And if you have a third electron, it would be here. Once you have all the electrons represented by arrows pointing up, then you will start putting the electrons pointing down. So the fourth electron would be, for P, would be pointing down in the first orbital here. All right. So, but we don't have 4 electrons. We have only 2 in P. This is what we are doing. Remember, don't get lost. We're representing this in the boxes here. We already did 1 S2 here. That's what we have here. 2 electrons, 1 pointing up, 1 pointing down. And the second energy level, which is this, we have S2. That means in sublevel S, you have 2 electrons, 1 pointing up and 1 pointing down. In sublevel P, which has 3 orbitals or 3 boxes, you have 2 electrons, 1 pointing up and the next one also pointing up. Now, let me tell you something. You remember that I told you the sublevels have numbers associated to them. We said that sublevel S is this number 0. So sublevel P is this number 1. Sublevel D is this number 2. Sublevel F is this number 3. Now, the orbitals also have numbers. And this, the center one, is always 0. Okay? So if this is 0, we have to picture this as a number line. Which number would it be this? Imagine this as a number line. Which number is this? We have 0 here.
1, well, +1.
This will be 1. Thank you very much. And this is going to be -1. Okay? So we have 0, 1, and -1. Let me ask you, in the case of D, what are the numbers that you will have in D? Remember that D has, how many orbitals will you find in D?
5.
So you have 5 boxes. 1. In chemistry, I don't expect you to understand everything at first. Now, I do recommend you to pay attention, because whatever you don't understand now, you will understand it later. But if you don't pay attention now, you will be lost later. It's okay to be lost now, right? I expect that. So this is D that has 5 orbitals. 1, 2, 3, 4, 5. Where would you place 0 here?
In the center.
In the center.
In the center. So
Okay. So which number is this going to be?
that's 2.
2. Next person. Which number is this?
-1.
-1. Which number is this? 1. And this is -2. So you do something like this. Okay, so I am trying to find out what are the 4 quantum numbers for carbon. Carbon has 6 electrons in all total. And it's that one.
Wait, Mr. Correa,
Yes.
my audio cut out for a minute and I didn't get to understand why the arrows point the ways they do. Could you go over
Okay.
that?
Yeah. I'm gonna explain that. I'm going to explain that. That's the last quantum number here. Okay. I haven't explained it yet. So I'm just trying to go over what we have done so far for those that might be more lost than the expected. I expect you to be lost, but not that much, okay? So carbon has 6 electrons. I do the electron configuration. When they ask me to write the quantum numbers for carbon, even though any of the electrons that you have here has the 4 quantum numbers, I always focus on the last electron that I put when I was doing the electron configuration, which is one of these 2. I just put 2 here. I don't know which one is the last. After I do this, I know which one is the last. Which one is the last electron that I place here? Huh? This, isn't it? Because, oh, something I didn't tell you, you always have to start from left to right. You start filling them up from left to right. 1, 2, 3, and then pointing down 4, 5, 6. All right, so look at this, please. Please look at this. I already found N, which is the principal quantum numbers, which refers to the energy level. This is asking you in which energy level is located that electron, energy level 2. That's why we have a 2 here. Okay, this 2 refers to the energy level where you place this electron. L refers to the sub-level. Remember, the sublevels are S, P, D, and F, but we are talking about quantum numbers. So I don't expect you to have a letter here. That's why they assign numbers to these letters S, P, D, and F. And these numbers are: for S is 0, for P is 1, for D is 2, and for F is 3. So anytime you have an electron in P, the quantum number, the azimuthal quantum number, or L, or secondary quantum number, as they call it also, is going to be 1. If the electron is located in D, then it's going to be 2. If it's located in F, then it's going to be 3. By the way, we have to go over this, how to do electron configurations for elements that reach up to D when you are filling up this thing. So M in this case is talking about the orbital. This is the energy level, this is the energy sublevel, and this is the orbital within the sublevel. And these are the orbital, the boxes. These are the orbitals, the boxes that you have here. So in this case, where did you place the last electron within P? Remember that this is P, this represents P. In which number, in which box number you place the last electron here? 0. So M equals 0. And S now refers to the direction of the arrow. S is the spinning. Something that I have to tell you is that even though you have the nucleus of the atom here, and then you have the orbitals surrounding this nucleus, okay, you have electrons surrounding the nucleus of the atom. They are moving like this, but they are also spinning on their own axis, like the Earth in the solar system. The Earth is surrounding the sun, is moving around the sun, but it's also rotating on its own axis. Electrons are doing the same thing. Now, electrons rotate clockwise or counterwise. If electrons rotate clockwise, then they will be represented with an arrow pointing up. And that is going to be represented with a number that is positive 1/2. Now, when they rotate counterwise, then the number is negative 1/2, negative half, okay? Arrows pointing up are positive half, arrows pointing down are negative 1/2. So this electron that we place here in 0 is pointing up or down? Up. And what is the number that we should write here? Positive or negative 1/2? Positive 1/2, because it's pointing up. Now, I'm gonna leave this alone here. I'm gonna leave it here, and I'm gonna do one more for example, vanadium. Vanadium, that is going to be 23, and I'm gonna do it here. Vanadium is 23. Please help me to do this quickly because we have 7 minutes. Vanadium, 23 electrons. Electron configuration is 1s2. Keep going. 2s2. What else?
P6.
P6. What else?
3s2.
S2.
D3.
I'm sorry?
D3.
No.
P6,
P6. And then
4s2.
4s2. And then you go back to the third energy level and you do D, how much? 3. I know with 3 because, you know, I have a very fast brain. I already counted them. All right, so this is what we have. If we have to do the quantum numbers for this, what are we going to write for vanadium as the quantum numbers? I'm gonna write here the letters that we write for the quantum numbers. There are 4, N, L, L, M, and S. In this case, what is N? What N equals to? Remember, N refers to the energy level where you place the last electron. What is the energy level where you place the last electron here?
4.
Bam, is 3. Remember, we did this, and after we did D3 here, okay? So this is the energy level where you place the last electron, 3. This 3 is not because you have 3 electrons here. This 3 is because it's in the 3rd energy level, all right? Don't be confused. L refers to the sub-level. What is the sub-level? What is the sub-level where you place the last electron here? Huh? In which, I'm sorry? In which sub-level you place the last electron? S, P, or D? We know that we are here, is in D. And what number is associated to D? D is 2. So whenever ends in D, is going to be 2, the L, the azimuthal quantum number. So that means L equals 2. M now refers to the orbital or the box where it's located. How many electrons are in D? 3. Okay, so I'm gonna draw now. I already drew the 5 orbitals for D, the 5 boxes for D. So now all I have to do is put the electrons. Remember, you will not do like 1, 2, 3, 4. It always up, all of them going up. And then when all of them have at least 1 going up, then you start putting the ones pointing down. All right. So I have to put 3 electrons in D. Already have 1, 2. Where do I put the 3rd one? Here pointing down or here pointing down?
In 0.
In the middle, pointing up. So in this case, fortunately, it's the same thing as in the previous example. M equals 0 because this refers to the orbital, to the box number where you place it. And then the S is the easiest one. All you have to say if it's positive or negative. In this case, it's positive or negative.
Positive.
So all I have to do is put 1/2. It's not positive because it's a positive number that you have here. It's positive because the arrow is pointing up. So in some cases, you'll have something like this. You have that this electron is pointing up here. For M would be -2, for example, if it's the case of scandium. It's -2, but for S is a positive 1/2 because even though it's in a negative box, is a pointing up arrow. So the spin is totally independent of this number up here. So these are the 4 quantum numbers for vanadium, all right? And this is how you find it. Now I'm gonna open the spot for any questions that you might have. Anybody has any questions? I'm gonna be silent for a couple seconds until you analyze this and tell me if you have any questions. Anybody?
Excuse me, Mr. Correa.
Yes.
Could you go back to the presentation? I wanted to get the definition of the quantum numbers.
The page with the definition of the quantum numbers.
Yeah, I didn't get the chance to get those.
Actually, this is not the definition of it. This is just giving you the 4 of them. The definition is all the way to the end. Let me see if I find it here. No, let me see if it's before this so that you can have the accurate one. Okay, this would be the definition for it. I didn't show it before.
It's okay, I got what I wanted.
Okay, you got it?
Yeah.
All right. I don't know if you want to have this also. And this, which is very important. Okay, I'm gonna stop sharing for a minute and I will stop the meeting because we only have 1 minute left. Join me back one time and we'll continue with this. After you come back, I'm gonna give you one for you to do on your own and then we are going to move on. So join me back one time as I resume the meeting.